identifying a quadratic pattern and finding the equation for it. So we're going to work through questions 2a and 2b, and then you will try 2c and 2d on your own. So part of the task is identifying a quadratic pattern, but for now we're going to assume that we know that these are quadratic, and we're going to explore what happens if you have a quadratic pattern. So on a spreadsheet, we're going to think about what happens if I just list numbers that are related to n squared. So if I just start with n and m, and I'm just going to explore what happens when I square those. So when I square the whole number, so 1, 2, 3, 4, 5, and here I'm actually going to list, n squared. So equals, and extend it all the way down. Okay, so I've just listed the square numbers, the numbers that are n squared. And just to see what happens, I'm going to explore what the numbers are going up in, what the differences are. So I'm going to do equals this number minus this number, and equals this number minus this number, and so on. And I can already see that this is not a linear sequence, a linear pattern. So that's the first clue. The first differences, the differences here are not constant, so it's definitely not a linear pattern. And I know it's not because it's n squared. So the first differences were not constant. But if I do the second differences, that minus that, and I extend the table, then I do actually get a constant difference. So the second differences are 2. So that's the first thing we're going to make a note of. The fact that if you have, so for quadratic sequences, so basically if the second differences are constant, then that means that the pattern is quadratic, i.e. it involves n squared. Okay, so that's our first clue. But we also want to see whether there's an actual link between this 2 and the n squared, and what happens if this is a different number. Now, to explore that, I've actually made a table listing not just n squared and 3n squared as well, and I've done my first and my second differences. Okay, so when the first difference is when the formula was just n squared, the second differences were 2. When the formula was 2n squared, the differences were 4. 4. When the formula involved 3n squared, the differences were 6. So you can probably already spot that this number is double the coefficient of n squared. So we're going to record that and then we'll just test it. So the other point to note from what we've just done is that the second difference in a quadratic pattern is double the coefficient of n squared. And let's just put it to the test. So if I list 5n squared, you should already be guessing what the differences are going to be. So I'm going to do equals 5 times this number squared. Let's try our first differences. So this minus this, and so on. Okay, so you should be anticipating that the second differences are going to be 10. Let's just see if they are. Equals this minus this, and it works. So we're going to use this to our advantage, because now we know if the second differences are 10, my formula involves 5n squared. If my second differences are 6, my formula involves 3n squared. In class, you'll look a little bit more at, we've looked a little bit more at why that happens, but for now, let's just use the technique. So let's put that to use in our first question, so 2a. Sorry, not 2b, 2a. All right, this is the table. So first of all, I'm going to copy it into here, n and m. 1, 2, 3, 4, 5. And 8, 17, 32, 53, 80. So I'm going to list my first differences. Let's assume at this stage I don't know if it's a quadratic or not. So let's look at the differences. So equals this minus 8 and extend all the way down. They're not going up. It's not a constant rate. So I'm looking at the second difference now. Equals this minus this. Okay, and the second differences are constant. So let's just make a note of what we found. The second, in blue, the second differences were constant. This tells us that it's a quadratic pattern, i.e. it involves n squared. And the fact that the second differences are 6 means that the coefficient of n squared is half of that, which is 3. So I know that my formula is m equals 3n squared. But it will also involve another pattern, now a few more terms. It's not just 3n squared, because 3n squared looks like this, and those are not the numbers I have here. So let's just generalize a little bit. If I've got any quadratic expression, it's going to be an squared plus bn plus c. Now I already know the value of the coefficient of n squared. It's just 3, but I don't know the rest. So for now, I'm just going to write plus bn plus c. Now, in order to find bn plus c, what I'm going to do is I'm going to subtract 3n from both sides. So minus 3n squared, and I get bn plus c. And I'm actually going to do that over here on my spreadsheet. I'm going to subtract 3n squared because I know that 3n squared is part of my formula, but I need to know what else is in there. So n and m. Actually, what I'm going to do is I'm going to copy the whole of this down to here. And I'm going to list 3n squared. So I'm equals 3 times n, which is just 1 in this case, squared, and I'm going to copy all the way down. Okay, and now just like as we said over here, I'm going to do m minus 3n squared. So equals m minus 3n squared, and extend it all the way down. Okay, so in this case, the value of this bit here, so bn plus c equals 5. Now what that tells me is that every time it's just 5. It's not, the numbers don't change, so that I don't need to actually find the value of b is actually 0. So in this case, the formula is b equals 3n squared plus 5. Okay, and I think the next example will make things a little bit clearer if they're not clear yet. Just to explain one thing, that this is sometimes referred to as the sieve method, a little bit like when you separate two different materials by using a sieve, a colander. And it's the same here, so you're removing 3n squared to see what else is in the formula. So the formula is made up of 3n squared plus 5. This is the formula for this column here. Okay, so to get 8, it's 3n squared plus 5. To get 17, it's 3n squared plus 5. And you can put it to the test, but we'll do that with the next example. Okay, so let's do the next one a little bit quicker. This is the next one. I've already prepared the table right there. So I'm going to look at my first differences. Equals, And then I'm going to look at my second difference. Equals this minus this. Okay, so once again, the fact that the second differences are constant means that it's a quadratic. The fact that it's 14, so the second difference is 14, means that my formula involves 7n squared. So m equals 7n squared, but I don't know the n term and I don't know c either. So I'm going to actually list 7n squared because I know that's part of the formula. Let's copy this table down here. So my first difference equals, and extend down, and equals this minus this, and extend down. And let's make sure we've got our labels. It's really important that you label your columns as you go along, because if not, you'll get really lost as to where the numbers are. That's not what I wanted to do. We've already got the second differences. Sorry about that. Let's just undo quickly. What we wanted was to list 7n squared. Okay, sorry. So equals 7 times this number squared. Right. So what I'm going to do if you think about it as a formula, is I'm going to subtract 7n squared from both sides to see what the bn plus c part of the formula is. And if you think of the terms in terms of the numbers, I'm going to remove these numbers from these to see what else is in the formula. I know 7n squared is part of the formula, but I need to know what else is in the formula. So I'm going to do m minus 7n squared. M minus 7n squared. Right, now this time it's not as easy as the previous example because the numbers are not just 5 like it was earlier, but I've got this sequence here, this pattern. So what I'm going to do is I'm going to take this pattern and I'm going to play with it over here. Now, if I do that, it just pastes the formula. So I'm just going to paste the values. That means it will just paste the values rather than the formulas that were in there. So I've got to figure out what this is. Now, this is bn plus c. That's the bit that's left over. That's the formula, this bit that I'm looking for. So I've got to find the formula for these. Now, to find the formula for these, well, I start the same way. I find my differences. So equals this minus this. The first differences were already constant. So I know that this part is a linear formula, linear pattern, and I know that it involves minus 3n. Minus 3 is the coefficient of that. So I'm actually going to list 3n because it seems that that's something that I will need. So 3 times 1 and list them. Okay. Right, so if you think about the formula, what I've got here, what I've discovered already, is that this part is 3n. So I know that my formula now involves 7n squared. I know that it also includes 3n, but I need to know c. So to do that, I'm going to do m minus 7n squared minus 3n, and that will give me the c value. So if I go back to my table, I'm going to do m minus 7n squared minus 3n. So equals m, this is where the labels are really helpful, minus 7n squared minus 3n. And I've done something wrong. Let's see, m. Oh, sorry, I know. The differences were minus 3. So let's just go back to here. Apologies for that. The differences were -3, so this should be a minus, and this should be a plus. So let's just go here. So I'm actually interested in -3n. Doesn't like a minus. Let's keep going, -3n. So that should have been -3n. Okay, and now my differences are all 4. So, in conclusion, I know that the formula is made up of, so m is made up of 7n squared plus -3n plus 4. Let's put that over here. So the formula is m equals 7n squared minus 3n plus 4. And we're going to put it to the test. So in the summative, you can be absolutely sure you've got the right formula. I'm going to write n, 1, 2, 3, 4, 5. And then I'm going to put my formula in, which is this one. I'm going to do 7n squared minus 3n plus 4. Fingers crossed it will be right. So 7 times n squared minus 3 times n. It doesn't let me click on it, so I'm going to just type in A21 plus 4. I'm going to extend it, and if you notice, I get exactly the same as the numbers that were in the original table. Okay, now just a few points to note here. Notice that you need to go all the way to the 5th term to get your second differences, or at least to the 4th term. It's not enough to go just up to 3 because you can't tell whether the second differences will be constant. All right, not easy, but give it a go. Have a go at B, at C and D. Press pause, and when you're ready to see the answers, press play. And here are the solutions. So this is, oops, that's the answer to C, 5n squared plus 3n plus 1. And that's the answer to D, 2n squared minus 9n. Thank you for listening.